there's gonna be some getting used to it.
Can you at home see it? Thumbs up. All right, cool. We're good.
Thank you. Sorry, guys. My apologies. The direction is the direction of the vector. Okay. Nothing too crazy here. Contrast that with a scalar, which only has a single component, right? Time would be a scalar. Whereas we might think of a displacement vector giving us both the distance traveled and the direction. And we'll deal with vectors quite a bit in here. Like I said, today is going to be more about, okay, let's get a common vocabulary. What do these things look like? And so one of the things when we get into the worksheet, you know, everybody's going to work at least one problem where you have to model the situation with vectors to figure out what's going on. It's really cool once you get used to vectors, the way they work and the amount of power they have, given how easy they are to use and manipulate. So let's take this situation. We'll make it very basic, right? Walk 3 miles north and 4 miles east. We've walked a total of 7 miles, right? That's our total distance. It's not our total displacement, though. Our displacement is a measurement from where we started to where we ended. So, walk 3 miles north, 4 miles east. This would be what we call our displacement vector. Here's one of the really cool things that we're going to love about vectors. What kind of triangle do we have there? We have a nice 90-degree triangle, right? And still getting used to the tech myself. Which means all of our right angle trig comes into play. Pythagorean theorem, right? That 5 miles, I didn't make that up. The square root of 3 squared plus 4 squared is 5. So all this stuff is going to bring back a lot of memories. We're gonna use trig a decent amount in here. I think it's really cool the way we see all the stuff you guys have built. You know, the trig, the derivatives, the integrals is all going to start to come together in this course. So when we talk about displacement, we're talking about how far do we go from our beginning to our ending, not necessarily how far our path of travel was. And guys, you know, if you have questions at any time, don't feel like you can't interrupt me. You absolutely can. Same thing goes for you guys at home. If I miss your question, Gabriel will pick it up. And if it's something he wants us to all talk about, you know, he'll let me know. So don't feel like you have to wait to ask any questions. So basically, visually what's going on, or graphically, the sum of two vectors comes from applying one vector to the other. And the question, you know, we could ask ourselves, well, does the order matter? You know, if I think, I'm trying to remember now, what did we walk north first and then east? We walked east first and then north. Do we get a different displacement vector, right? Oops. So here would be a case where maybe we have two different people. Actually, let me back up a little. Let's talk about whether or not the order matters first. All right, situation one. We went 3 miles north, 4 miles east. There was our displacement vector, right? That was what we saw on the previous slide. Okay, now we go 4 miles east, 3 miles north. There's our displacement vector. These are the exact same vector. They point in the exact same direction and they have the exact same magnitude. Now, they're in different spots on the board, but that doesn't matter. The only thing that makes vectors the same is if they have the same direction and the same magnitude. They do not have to have the same starting point or ending point. So the order doesn't matter. Well, let's take a step back and think about why that makes sense. Well, basically, when we apply one vector to the other, we're adding them. And think about addition, right? 2 plus 3 is the same as 3 plus 2. Same thing works with vectors. Now, this will give us a different situation. Let's say we had two different people. One person goes north, the other person goes east. Now we have two possibilities depending on where we're starting and ending. But you can see we're not going to get the same displacement vector as over there, right? It's got a different angle. It's going to have the same magnitude. But if we start down here and go up, that gives us one option. Or if we start up here and go down, that actually gives us a different vector because it's actually pointing in a different direction. So this is more like subtraction. Because if you think of the way subtraction works, changing the order changes the sign. Changing the order that we count first changes the direction of our vector. So there's all these nice analogies to our basic arithmetic. This we talked about before. Doesn't matter where a vector starts in the plane. The only thing that matters is its angle and its magnitude. So that is the same vector as that. That's always going to be the same vector regardless of where it starts. That'll be important as we go on and we start to talk about whether vectors are the same, they're parallel, what does it mean? This to me is one of the most important things we'll talk about today. And one of the ideas I want you to take with you going forward is the vector being made up of components. You're going to hear me talk a lot about that in this class because it is a really interesting way of making sense of vectors. And even some of the problems that will work in the worksheet, being able to break it into components helps us make sense of it. So let's call this vector V. It's got two components. It's going to have, now if we're on the XY plane, it has a horizontal component and a vertical component. And those two components are perpendicular to each other. The reason this is important is because we may want to know the influence of a vector in the direction of another vector. Well, then all we need to do is break that initial vector into its components, one of which is parallel to our direction of interest and the other which is perpendicular. Because when we look at the component that's in our direction of motion, it's influencing our motion. But if it's perpendicular, it has no effect. So this idea of breaking a vector into components, you'll hear me harp on this when we do dot product and later this semester when we look at directional derivatives. But the idea is basic. It is just, there's two components to any vector. Those are the two components that made up that right triangle. And that's really nice because that's where all of these nice right triangle properties come out. You know, the Pythagorean theorem and all our right angle trig. So there's our right triangle again. So we'll do, that's something we'll do more of as we go on. Again, this is just getting us some of the verbiage. You'll hear me say stuff like, well, what about the components of that vector? All right. Just a couple, we have two different notations of vectors. I want to talk a little bit about each because you're going to see both in here. You're going to see both in the homework. You're going to see both as you guys go on and take physics and take other math courses. Depends on the teacher. I do not mind you guys using either form, but let's just talk a little bit about them real briefly. So we have so in 2D, a vector has two components like we were just seeing. You're going to see me, this is typically how I like to write vectors with the angled brackets v1 comma v2. This is 100% the exact same vector right here. And what's happening here is the components are being multiplied by a unit vector in the horizontal and vertical directions. So these mean the exact same thing. Whatever you guys are more comfortable with. And again, you'll see both in the homework, you'll see both in the worksheets. There's nothing wrong with being able to go back and forth flexibly, but when it comes to you doing your work, you pick whichever one you like better. Yeah.
What is it you said? I mean, multiplied, what is the verbiage?
Oh, yeah. So oh, that's the wrong board. I and J are unit vectors. So I is a unit vector in the horizontal direction. I'm using my hand. So I is a unit vector in the horizontal direction. So it's saying, okay, we're going to multiply that component by the horizontal component because that's the direction that it's in. And then the J represents the vertical. Okay. So the way that it's kind of, you know how like an ordered pair you have X, Y. This works very similarly, horizontal, vertical, horizontal, vertical. The one thing I do want you to be careful of, and it's because I see it, and you know, it's one of the things that we'll keep an eye out for when we're working on problems. Don't mix the two together. Okay, what I mean is, don't do something like 3i and plus 4j with those brackets, because that doesn't have any meaning, right? It loses what the construct means. And in fact, even if I put the comma in there, this is not the same thing as 3, 4, right? So when you use the angled brackets, you do not need the I and J, you do not need plus. You kind of treat it almost like a point. If you do the other form, so this would be the same as 3i plus 4j, then you do need a plus, and you know something that shows that the I and J are vectors. You can see they got the little arrows over top. These guys here. Did it again. Those you'll sometimes hear those called hats. So some people refer that to I hat and J hat. And some people, again, you'll see some variety here. Now, this is something you won't see me do, but sometimes you'll see like this. It looks a little bit more like a hat there than when you have the arrow. You know, I tend to find, you know, we all tend to do what we did when we were in school. And, you know, all my professors use this form, so that's kind of how I've always done it. But guys, this is 100%. There's nothing wrong with either of these. Personal preference. Use whatever you're most comfortable with. We're going to have vectors in 3 space. This is multivariable calculus. We're going to be looking at things in 3D. All the stuff we've talked about so far, all we're doing is adding a third component. Now, we're going to get into some differences later when we start doing multiplication and cross product and dot product, but that's not till next week. So for right now, all we need to know is, hey, we're going to look at vectors in 3 space, right? That would be a vector in real life. You know, for example, like this pen could be a vector, right? Has a beginning and an ending, has a magnitude and a direction. So we will need some 3D vectors, and you know, we'll do a little bit of it in here. But one of the powers of vectors is they can be expanded into n dimensions. So we have a 3D vector, we can make 4D vectors, we can make nd vectors if we need them. So, all right, one last thing to talk about. Again, just make sure we're talking about things the same way. All right, what does all this mean? Well, let's talk about it real quick. The first one is saying something we've already said. This one up here, that's saying to add 2 vectors, all you do is add their components. To subtract 2 vectors, all you do is subtract their components. Now, this is only on a 2D vector, but that's the same for a 3D vector or an ND vector. So adding and subtracting vectors is as easy as you would think it is. You just add up their components or you subtract their components. That's going to be when we, on some of these problems on the worksheet, you know, my advice is going to be to model make a diagram with your vectors, because, hey, are you just adding vectors? Well, then you just add them together. Or are you subtracting vectors? Then you just subtract the components. So from a math standpoint, vectors are very easy to work with. Scalar multiple. So this guy here, we'll see this guy a few times this semester. This is called lambda. A lot of times it's used to represent a scalar. Later this semester, you know, we'll be using it to represent a Lagrange multiplier. Basically, think of it this way. It distributes over the vector. So if you want to double the length of a vector, you just double all of its components. If you want to cut a vector in half, you cut all its components in half. That's all that's saying. So this is just the mathy way of saying this. And again, remember, guys, and for you guys at home too, PowerPoints are 100% available for you. So don't feel like you have to take notes on everything that's up here. Just get the relevant stuff. Last thing, magnitude of a vector. That's that Pythagorean theorem we were talking about. And that becomes incredibly useful for a few reasons. Number one, we might just want the magnitude of a vector. For example, if what we have is a velocity vector, the magnitude is the speed. We can also use it to find what's called a unit vector. A unit vector, and I know we don't have it defined on here, but I'm going to ask you to do something like this in the worksheet, so let's talk about it. A unit vector is a vector that is in the same direction as a given vector, but only has a magnitude of 1. The reason that is so useful is what it does is it preserves the direction, but gets rid of the magnitude. So when you're talking about things like a dot product and you want to know the influence of one vector in the direction of another, you're going to see us use a unit vector a lot because all we want is the direction. We don't want the magnitude. So now here's how nice this is. I got a vector up here. Let's give it a name and not use that color. Let's call this guy V, because that's what we've called every vector so far. All right, very simple question. What is the magnitude of V? And you can actually tell me how to find it if you want. What do you get? 5. All right, so I got an answer 5. What do you guys think? So here's how we would do this, right? Square root of the sum of the squares. It's just Pythagorean theorem. Square root of 25 or 5. There is our magnitude. That's what these double bars along the side of a vector. Some books only use a single bar on both sides. Yeah, I've seen that as well. I use double bar. That's the magnitude of this vector. All right. Well, let's say I want a unit vector that's in the direction of V. Okay, so I want a vector of magnitude of 1 that's in the same direction as the 3, 4 vector. I'm going to combine two of the things that we just did on here. Number one, I know I want it in the direction of V, right? The problem is the magnitude of V is 5. But I want the magnitude to be 1. So what I'm going to do is divide by the magnitude of V. Right? That's going to take care, because I know the magnitude of this is 5, and I'm dividing by 5, and the magnitude has to be 1. This is going to create what we call a unit vector. Now here's where it's going to look similar to something on there. We know that this is 5, right? So this would be the same thing as 1/5 times our vector V. That's our scalar times V. Well, we know how to do that. 1/5 times 3, 4. That's it. I mean, we're done here. Or if we want, we know that that scalar distributes. 3/5 forfeits. What we have is a vector that is in the same direction as this one. That means they're parallel. We know they're parallel because they're a scalar multiple of each other. And we also know, because that scalar multiple was the reciprocal of the magnitude, we're guaranteed that this thing has a magnitude of 1. So again, what I think is really cool about this, not just today, but this course in particular, we're going to be pulling stuff like the Pythagorean theorem that you've been doing over the past few years of your math career, and seeing how we can leverage those to work more interesting problems. Questions about that? Now, here's the nice thing. If I said, hey, I want a vector parallel to this with a magnitude of 700, what could I do now? Yeah, I could, I know you guys didn't hear them, but this is a unit vector. All I got to do is multiply this vector by a magnitude of 700 or whatever magnitude we want, right? So this process of turning it into a unit vector preserves the direction. And because it only has a magnitude of 1, we can give it any magnitude we want just by multiplying it by a scalar. And now I did this in a 2D case, but this expands, this extrapolates to 3D and so on. Okay. Questions at this point? Let's do some problems. All right, we're going to do some problems. Let me see. I got some worksheets here. And for us in here, I'm going to encourage you guys to work together. I'm not going to require it, but it's always nice to have a partner or a small group to work with, just to ask questions. And what we'll do is we'll use the boards and put up our solutions. Now, we're not trying to get through all 7 of these. So I would like, everybody to try number 1. And then maybe we'll split up some of 3 through 6 so that you get to try one of those application problems. But guys, you do not have to work at the desks. If you want to work at the boards, that is totally fine. I mean, this class space is ours. However, you guys, if you want to move around, feel free. Because ideally is we'll put our solutions on the board. That way we can see each other's work and ask questions. Hey, how'd you get that on 3? Oh, okay. And then that's what we can take a picture of and share in the forum. So again, I will never force you to, but if you would like to go work at the boards, feel free. You guys can group up. And I'll be quiet. And I will say this. There is one other advantage of you guys working at the boards that is valuable. I can see what you're doing. I can't see what you're doing when you write on paper, but you're working on the board and maybe you're going in the wrong direction, or I've got a hint. It makes it a little bit easier for me to say, oh, careful on this right here. Maybe we just change that. It's a little harder on paper, because then you got to call me over and we got to look at it. So I'm going to try to encourage you guys to work at the boards, but again, I'm not going to push it. We got all this space. You guys have been sitting for an hour.